Calculus Lesson 1. Things change. Some changes are chemical, some are physical. A chemical change is one where the substances undergo a rearrangement of the atoms and molecules through however they are bounded. Physical changes are changes of position, time, orientation, image, shape, and other such physical actions, which manipulate the substances. Despite being different, these changes have similarities. It is therefore important that we ask what change is. The purpose of mathematics is not to solve problems of physics and chemistry. Mathematics has its own goals which are different from the other sciences. The purpose of mathematics is to understand the structure of knowledge, facts, thinking, while omitting the particular facts, knowledge, or thought process. For example, physics says 1 electron charge plus 1 proton charge equals no charge. Chemistry says 1 electron plus 1 positive hydrogen ion yields a neutral hydrogen. Art says harmony in nature and draws a picture of it. Math says 1, omitting the thing, plus -1, omitting the thing, equals 0, omitting the thing. Then, mathematics says, given 1 plus -1 equals 0, what can we understand about the nature or perception and conception of this fact? The purpose of calculus in that field of mathematics is to study the nature of change itself. Change necessitates a relationship between two or more quantities. But change never happens in a vacuum. That change from one quantity to another happens over time, or space, or both. So to understand change in reality, we need calculus and the study of functions. A function is the relationship between two or more quantities, such that one quantity has a value which depends on the value of a different quantity. The former quantity is called the dependent variable. The latter quantity is called the independent variable. How a function evolves is the study of calculus. To understand how it evolves, we need to have some knowledge of the domain of the independent variables. Essentially, we need to know where the independent variables live. If it is not explicitly stated, we use what is called the domain convention, which is that we assume that when not stated, the home of the independent variables, the domain of them, is all real numbers. A real number is one which can exist as a decimal, which either goes on forever or comes to a stop. Therefore, a real number can either be rational or irrational. Some domains, like say if our domain was based on atoms, we would have to have whole number domains only, as there are no fractions or irrationals in atoms, only whole numbers. A function, denoted f, is such that each input, each independent variable, results in or is related to exactly one output, or dependent variable. The given set of rules to convert inputs into outputs under identical conditions cannot change answers. Given the same question and content, for example, the function is add 1. f of x equals x plus 1. It cannot be the case that sometimes f of the value 1 equals 1 plus 1, which equals 2, and sometimes the result is the function of the value of 1 equals 1 plus 1 equals 3. The function must be such that each member of the domain only gets one partner in the codomain, or range. The codomain, or the value of the dependent variables, can have multiple partners in the domain. For example, the sine wave equation, f of x equals sine x. Graphically, it looks like this. So we can see that in the domain, x1, x2, and x3 only have one value tied to them. However, y1 has 3 values tied to it, and that's perfectly acceptable. If we wrote this as set Venn diagrams, it looks like this, and we can see that each independent variable only gets one arrow, which is what we want. So we can see here that there are different visual models of this relationship of the function between the dependent and independent variables. The one model that helps us visually more than the other is the graph. The graph consists of input-output points represented on a plane whose dimensions represent unitary value changes of the concepts that are defining them. For example, the function of driving a car at a constant speed, where the input is time in seconds, and the output is distance traveled in meters. If the velocity was not constant, we would instantly see that on the graph. Because a function cannot randomly change results given a set of rules, there are many functions which have similar appearances to each other because they have similar rules. Here are the 12 basic graphs of functions. F of x equals a constant. F of x equals x. F of x equals x squared. F of x equals the square root of x. Likewise then, we also have f of x equals x to the power 3. F of x equals the cube root of x. F of x equals 1 over x. F of x equals 1 over x squared. F of x equals the square root of 1 minus x squared. F of x equals the absolute value of x. And then there are combinations, like f of x equals 1 plus the square root of x minus 1. Or the rational functions, f of x equals 2 minus x divided by x minus 1. The function of functions. Since a function on a set of input elements x is just a rule that assigns a unique element f of x, which is a set of possible output elements to each input element, then there must be an infinite amount of combinations of inputs, rules, and outputs. However, we can still detect patterns in the general nature of functions. For example, there are what we call even and odd functions. An even function is one where the negative input is the same as the positive input, such that f of negative x equals f of x for all of the x in the domain. As an example, f of x equals x squared. So if we put in a negative x, we would get negative x squared, which equals negative 1 squared times x squared, which is equal to x squared, which is the exact same thing as if we had just put in the positive input. An odd function is one where the negative input is the same as the negative of the positive input, such that f of negative x equals negative f of x for all of the x in the domain. Functions can also be added together, subtracted from each other, multiplied, and divided, except when the denominator is 0, in order to produce new functions. We can also put a function into a function. Functions come in many forms. Let us examine some. Find the domain, codomain, symmetry, is it even or odd, if any, of the following functions, and then graph them. 1. F of x equals x squared plus 2. 2. F of x equals the square root of 2x. 3. F of x equals x plus 3 cubed. 4. F of x equals 2 divided by x plus 2. F of x equals x squared plus 2. we can set up a t-table. X goes here, f of x here. If we plug in a 0, we'd get 0 squared plus 2, which is 2. We plug in a 1, get 1 squared plus 2. 1 squared is 1, plus 2, 3. We jump, let's jump to 5. 5 squared plus 2, 25, so that'd be 27. If we go to the negatives, -1, let's go -5. -1. -1 squared plus 2. -1 is 1. 1 plus 2, 3. Likewise, -5 squared, 25, 27. So, if we were to graph this, we find at 0, at x equals 0, this is x, this is y. At x equals 0, y equals 2. So we have a bump there. At 1 plus 1 or minus 1, we are at 3. That's 2, 1, 2, 3. But then plus or minus 5, let's go. It's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All the way up, let's say 27. So our graph will look like that. So then we want to know what is the, let's clear the space up here. What is the domain? The domain is the stuff on the x-axis, and it can go all the way left and all the way right. So we're just going to say all real numbers. The codomain is the stuff on the y-axis. And it's going to go all the way up to the left forever, all the way up to the right forever, but it stops here, and we get nothing below that area. So the codomain, we can say, is 2 less than or equal to y, which is less than infinity. So y, all of the stuff that exists that will have a y component, is between 2 and infinity. Symmetry. Yes, we have here a mirror-like effect at, we have what is actually in fact called an even function at x equals 0. Okay, so we do it again. So we have a t-table we will build. X, f of x. What we put in here. Okay, first let's just notice this. If we put in a 0, we get a 0, because the square root of 2 times 0 is the square root of 0, which is 0. We put anything negative, however, -1, say, the square root of -1 is called I and belongs to the complex plane, and we are not dealing with a complex plane. So therefore, x cannot be less than 0. So all of these numbers are going to be positive. So +1, +2, positive, let's go 8. So if we put 1 in, 2 times 1 is 2, so we'd get the square root of 2. If we put 2 in, we'd get the square root of 2 times 2, which is 4, and the square root of 4 is 2. We say 8, that'd be 2 times 8 square root, which is the square root of 16, which is 4. So if we were to graph this, we're getting nothing on this side. It starts at 0. 1, 2. At 1, we get the square root of 2. At 2, we get 4. But then by 8, we've only gone, at 4 squared, we get 2. By 8, 1, 2, 3, 4, 5, 6, 7, 8. So this curve kind of going off that way. So the domain. What is the domain of f? It stops at 0, so it's less than or equal to x, and it goes on forever. The codomain also starts at 0, also goes to infinity. However, that infinity takes a lot longer to get to, but still, let's say, 2 times, so 2 times that, it's a big number, we're going to infinity. Symmetry. Is there any symmetry? No. Okay. F of x equals x squared plus 3 cubed. We do our t table. And what do we get? Let's plug in, let's start over in the negatives. So let's start over, let's go -5, let's just write them all out. -5, -4, -3, -2, -1, 0. Let's check going. 1, 2, 3, 4, 5. All right. -5 plus 3. Then cubed. So in that case, also -4 plus 3 and -3 plus 3. So we can see we have a pattern here, which will be that it's -2 cubed, -1 cubed, 0 cubed, 1 cubed, 2 cubed, 3 cubed. Let's keep going. 2, right, this one, let's 5, 4, 3, 2. Two, 1, 0. Yeah, that makes sense. Okay, 4 cubed, 5 cubed, 6 cubed. What do we have? 7 cubed, so on. So what is 2 cubed? That is -2 times -2 times -2. -2 times -2 is +4 times by -2. That gets us -8. Likewise, when we have 2 cubed here then, but they're all positive. And so let's just keep going here though. 1 cubed minus 1. Minus 1 times -1 times -1. 0 times 0 times 0, 0. 2 minus 2 plus 3, +1. 1 times 1 times 1, 1. 2 cubed, 8. 3 cubed, 3 times 3 times 3, 27. If we went -3 cubed, then we'd have -27. So we don't even need these ones. We know the pattern. Let's fill out the pattern in a graph. So our graph goes on the x and up the y at -5 or at -8. -4 we're at -1. At 3, -3, we are at 0. -2, -1, -2, we are at 1. At 1, we are at 8. At 0, we are at 27. We have the chart. So let's just connect these dots. Something like that. All right. Questions. We have the domain. What is it? Domain is everything on the x-axis. This is going to continue left, continue right forever. So let's just say all real numbers. The codomain is the y-axis, and we're going to go down forever and up forever. And we didn't stop anywhere, so all real numbers. Symmetry. Is there symmetry? There is a type of, it's a type of rotational symmetry going on, which is what we get when we have odd functions. And so it's odd about x equals -3. T-table. Okay. So let's see first and foremost here, what happens if x is equal to -2? X equals -2, and we have 2 over -2 plus 2, that is 2 over 0. If I have two objects, one here and one here, and I want to divide them into 0 categories. How can I do that? I can't. Undefined. You cannot define what it means to divide two things by 0 amounts. So, that is undefined at that point. So, let's say, straight up, that f of x cannot... Let's put it this way. Let's say -2 cannot belong to f of x. Or, more appropriately, cannot belong to the domain of f of x. I'll just put it in brackets. Simple way of saying that, x cannot equal -2. Well, let's make that look nicer. X cannot equal -2. What happens when it is more negative than that, though? Let's go -3, let's do a -4, and then let's go less negative. -1, and 0. See what we get. So if we plug in a -3, 2 over -3 plus 2, we'd get 2 over -3 plus -1, -2. Okay. If that's a 4, then that is a -2, and that's a -1. See what's happening on the other side for now. 2 over -1 plus 2, that's 2 over 1, which is 2. And if we plug 0 in, and that's plus 2, just call it right there, 1. If we were to start to graph this, that x, that y, we need to make sure that at -2, there is a hole, essentially, in the map, such that there could be no spot that touches that line on the y-axis. That's what it means to be undefined. So at -3, we were at -2. So we're down here somewhere. So that's -2, that's 1, then that's 1. That's 2, then here. Put it there. At 4, -4, we are at -1. At, let's just plug in -5 for now then, and see what happens when we go one more over. That would be 2 over -5 plus 2, which is 2 over -3. So that is about 66.6 repeating percent. Or 0.66 repeating. If we plug -6, then this would become -4. All right? 2 over -6 plus 2, -4. So as we make this number larger, the negative value down here is also going to get larger. Gets bigger and bigger. And let's say we put, some big negative value here. We're getting closer and closer to 0, but never touching 0. Which also means if we get closer and closer to -2, let's get rid of these ones. Let's go right up against -1, or negative, we're going from this side, let's go -2.001. So that's 2 over -2.001 plus 2. That would be 2 over 0.01 negative, which is like -200. So actually on this side, it's getting closer and closer to that, and then goes that way. We saw when this was a -1 that we had, what did we have? 2 over -1 plus 2. That's +1, so that's 2. And then 0 is 2 over 2, just 1. So we can see that we actually have the same thing happening on the other side. At -1, we are at +2. At 0, we are at 1. So we're going in the other direction. Don't touch the line. All right. That, therefore, is our graph. So, question. What is the domain? The domain is the x-axis stuff. And we're going, obviously, to -infinity on this side. And over here, on the top there, we're going to infinity. However, we can't cross across -2. So our domain is went a little crooked there. -infinity less than x less than -2. And -2 is less than x, which is less than infinity. Or you can even, shorthand all real numbers except x cannot equal -2. It's not really all real numbers. But codomain. Codomain is the y-axis. It's going to -infinity. It's also going to infinity, but it's not crossing the 0 line. So in that same way, -infinity is less than y, which is less than 0, and 0 is less than y, which is less than infinity. Two functions. Find the domain of the following functions: f plus g, f minus g, f times g, f divided by g, and g divided by f for the following. 5. F of x equals x, g of x equals the square root of x minus 1. 6. F of x equals the square root of 1 minus x, g of x equals the square root of 1 plus x.
Okay. Question 5. F of x equals x, g of x equals the square root of x minus 1, and we want to put in the functions. We want to add the function, subtract the function, multiply, and divide, and see the different combinations. And then get the domain and the codomain. So let's start with A, f plus g, f of x plus g of x. So that's x plus the square root of x minus 1. Simple as that. B. B is f of x minus g of x. X minus square root of x minus 1. Easy as that. Alright, multiplying. In this case, x equals x minus 1. We could always put that inside, in which case we would get the square root of x would be x squared. Like that. Oops, put a bracket there. And then he would have been foiled in at some point. So you can write it like that. But let's just keep it like that. All right, D. F of x divided by g of x. Okay, well that's x. And that is the square root of x minus 1. Typically, we do not like to have a square root in the denominator. So what we can do is we could times both sides by 1, because that doesn't change anything. But we can also make it such that that 1 is the square root of x minus 1, right? The square root of x minus 1 over the square root of x minus 1, that is still technically equal to 1. So we still haven't done anything to the equation, except for we have removed the bottom square root. A square root times a square root is the thing inside the square root without the square root. And then on the top we will get basically what we have for C. X times the square root of x minus 1. So let's write that. Let's write that right here. All right, and then let's find E. G of x over f of x. It's fine on that one. Let me rewrite that here. G of x over f of x. So that is the square root Easy enough. Okay, let's go back. This is A. This is B. C. D. And E. Let's ask ourselves, what is the domain and codomain of this? Well, what happens when x is 1? If x is 1, we get 1 plus the square root of 1 minus 1, 1 plus square root of 0. That equals 1. If we go any further, though, say, well, if we do any positive numbers, we're fine. If we do 0, however, 0 plus minus square root, that gives us I, complex plane. We don't deal with complex planes, not yet. So x cannot be less than or equal to 0. So the domain, therefore, I could say, is 0 less than or equal to x less than infinity. You can put in any really big number, because 2 minus 1 is fine, 3 minus 1 is fine, 4 minus 1 is fine, and so on. So the same is true for this. It's the exact same issue. Okay, this one, same issue. This one has two different issues. If x is less than negative, if x is less than 0, then we get that same problem, but we also have if x is 1. However, we could have 0.5. All right? Or no, actually, let's fix this. These should all be 1, but not equal to. Same with this one. And x cannot equal 0, but it could already not be less than 1. So I think that applies to all of them. Oh, did I not even write those down? Okay. Question 6. F of x and g of x, we want a f plus g. F plus g in this case will be the square root plus the square root. If we do b, it's f minus g. It's the same thing, except we get minus the square root of 1 plus x. C f times g, square root of 1 minus x times square root of 1 plus x. We can try and solve this one, make it simpler. Let's do that by making these exponents of half powers. By doing that, we see that we should be able to put these together that. Can you do that? Does that make sense? Then we get square root 1 squared, negative x's, negative x plus x, negative x squared. Those cancel, and we are left with 1 minus x squared. Okay, yeah, that works. Yep. I got it right. Okay, so that equals, let's put it up here. Let's just swap this. And just get rid of this. Okay. D. F divided by G gives us 1 minus x, 1 plus x. We boot the root by timesing both sides by that denominator. So we just did what was on the top here, and we found that that's the square root of 1 minus x squared. And the bottom is 1 plus x. Let's put that right here. Perfect. And E, G over F. It's the opposite. So that will be square root of 1 plus x over the square root of 1 minus x. Should get us basically the same thing here. The square root of 1 minus x squared on the top, but 1 minus x on the bottom.
Composite functions. 7. If f of x equals x squared plus 5 and g of x equals x squared minus 3, find the following. F composite g of 0, g of f of 0, f of g of x, g composite f of x, f composite f of minus 5, g of 2, f of x, g composite g of x.
If f of x equals x squared plus 5 and g of x equals x squared minus 3, then find the following. F composite g of 0, g composite f of 0, or g of f of 0, f of g of x, g of composite f of x, or g composite f of x, f composite f minus 5, g of 2, f of x, g composite g of x. Starting with A, f composite g is the same as f of g of 0. So we want to plug 0 in for g. So let's actually just write out what g is inside of f. So this is g, but we are replacing the x with a 0. 0 squared minus 3. Well, 0 squared is 0 minus 3 is minus 3. So we are looking for f of minus 3. So we plug minus 3 in for f of x. And what we will find then, negative 3 squared is 9. 9 plus 5 is 14. Let's say f of g of 0 equals 14. B, g of f of 0. So we do the same thing, but we plug the 0 into this one first. So let's write g of 0 squared plus 5. If we just solve that for now, g of 0 squared is 0 plus 5, so g of 5. Plug 5 in for this, and what do we get? We get 5 squared minus 3. 5 squared, that's 5 times 5. That is 25. Minus 3, 22. All right. C. F of g of x. So we had, as before, f, g is x squared minus 3, but we have nothing to replace it with. Keep it as an x. Next step then is to plug this whole thing into that x. So we would write bracket x squared minus 3 and bracket squared plus 5. This thing is inside this x. So we have to times this by itself. So we can use the FOIL method. First terms, outside terms, inside terms, last terms. If you don't know what that means, we are going x squared minus 3 times x squared minus 3. Those are two terms. That's why they're squared. The FOIL, first terms, x times x squared times x squared. That is x to the power of 4. Outside terms, x squared times negative 3. That would get us negative 3x squared. Inside terms, negative 3 times x squared. Same thing, negative 3x squared. Last, negative 3 times negative 3. That is positive 9. So, from our FOIL, we would get x to the power 4 minus, put these together, minus 6x squared plus 9, and then don't forget the 5, plus 5. So that is actually, if we put these two terms together, our answer. x4 minus 6x squared plus 14. D. G. Composite F, which is just G of F of X. So, same thing, but in reverse. So this time it will be G of X squared plus 25. Oh, not 25, jumping ahead of myself. Just 5. But then this goes inside of the G, which will be bracket x squared plus 5 squared minus 3. F is inside of G. So we have to do the same terms, same FOIL, but this time we have positive 5s. So we get x to the 4, 5 plus 5 will be 10, 10x squared, 5 times 5, 25. So when we put it down here, we will have x to the power 4 plus 10x squared plus 25 minus 3. Don't forget the minus 3 from the G. So if we simplify that, 25 minus 3 is 22. I've got two different 2's going. 22. We can see then, if we plug a 0 into these equations, we'd get 0 to the power 4 minus 6 times 0 squared plus 14, which would equal 14. To put a 0 to this one, we'd get 0 to the power 4 plus 10 times 0 squared plus 22, which would equal 22, just right here. F of negative 5. So we plug F, we do this one first. So that is minus 5, put that in brackets, squared plus 5. So we can solve that, and that would be negative 5 squared is negative 5 times negative 5, that is 25. Plus 5, that's 30. So f of 30 don't need the f anymore. I want 30 squared plus 5. 30 times 30. 0, 0, 0, 9. 900. 905. Let's put that right here. F. G of 2. G of 2. So G is x squared minus 3, so that's 2 squared minus 3. 2 squared is 4. 4 minus 3, G of 1. G of 1. So we plug 1 squared minus 3. 1 squared is 1. 1 minus 3, that is negative 2. G. F of x. F of x. So we just plug the whole thing in to one of them, f, and then we do it again, which will be, say, bracket x squared plus 5 squared plus 5. We've already seen what this is. That is x to the power 4 plus 10x squared plus 25 plus 5. So we can simplify these. That's 30. And let's just put that up here. X, I can write neater than that. And H. G of x. So that is, if we just write it right off the bat, x squared minus 3 squared minus 3. We've seen this one before. That's x to the power 4 minus 6 x squared plus 9 minus 3 from that guy. So this simplifies. 9 minus 3 is 6. And that will be our G. You can then take these numbers, minus 5 and 2, and plug them into G, and see if you get the right answer.
The continuity and limits of functions. Continuity, the state or quality of being continuous. Continuous, uninterrupted in time, sequence, substance, or extent, of or relating to a line or curve that extends without a break or irregularity. Given an interval I, we say that the function f is continuous on the interval I if it is continuous at each point of I. Given a point C on the interval I, we say that the function f is continuous at an interval point C of its domain if, as the limit of x approaches C of the function f of x, the limit will equal f of c. If either the limit fails to exist, or it exists but is not equal to f of c, then we say that f is discontinuous. Limit: the value the function approaches as its independent value approaches a certain value in the domain. For example, in the function f of x equals x squared, as x approaches plus 2 from either direction in this case, then the function f of x approaches 4. We write the limit equals the limit as x approaches a of f of x, in this case the limit as x approaches positive 2 of x squared, which equals 2 squared, which equals 4. Definitions and theorems of limits. Definition: formal definition of a limit. We say that f of x approaches the limit L as x approaches a, and we write the limit as x approaches a of f of x equals L, if the following condition is satisfied. For every number epsilon, which represents allowable error, which is greater than 0, there exists a number delta, which represents a difference tolerance, which also must be greater than 0, possibly also depending on epsilon, such that the absolute value of x minus a is greater than 0 but less than delta, then x belongs to the domain of f, and the absolute value f of x minus L is less than epsilon. Definition of a right limit. F of x has a right limit L at a. Written, the limit as x approaches a from the right of f of x equals L, if the following condition is satisfied. For all epsilon greater than 0, there exists deltas greater than 0, such that if a is less than x, which is less than a plus delta, then the absolute value of f of x minus L is less than epsilon, and x belongs to the domain of f. Left limit. F of x has a left limit L at a. Written, the limit as x approaches a from the left of f of x equals L, if the same conditions of the right limit are satisfied. Theorem 1. A function f of x has limit L at x equals a if and only if it has both left and right limits there, and these one-sided limits both equal to L. Theorem 2. Limit rules. If the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m, and k is a constant, then 1. The limit as x approaches a of f of x plus g of x equals L plus m. The limit as x approaches a of f of x minus g of x equals L minus m. The limit as x approaches a of f of x times g of x equals L times m. The limit as x approaches a of a constant times the function of x, that will equal the constant times L. The limit as x approaches a of f of x divided by g of x equals L divided by m, if m does not equal 0. 6. If lowercase m is an integer and lowercase n is a positive integer, then the limit as x approaches a of f of x to the power of lowercase m divided by lowercase n, then this will equal L to the power of lowercase m over lowercase n, provided that L is greater than 0 if n is even, and L does not equal 0 if m is less than 0. Rule 7. If f of x is less than or equal to g of x on an interval containing a in its interior, then order is preserved and L will be less than or equal to m. Theorem 3. The squeeze theorem. Suppose that f of x is less than or equal to g of x, which is less than or equal to h of x, which holds for all x in some open interval containing a, except possibly at x equals a itself. Suppose also that the limit as x approaches a of f of x equals the limit as x approaches a of h of x, and these two equal L. Then the limit as x approaches g of x equals L also. Limit examples. Evaluate the limit or explain why it does not exist. 8. The limit as x approaches 4 of x squared minus 4x plus 1. 9. The limit as x approaches negative 2 of the function x squared plus 2x over x squared minus 4. 10. The limit as x approaches 9 of the function square root x minus 3 all over x minus 9. 11. The limit as h approaches 0 of the function h plus 1 squared minus h minus 1 squared all over h. 12. The limit as t approaches 1 of the function t squared minus 1 over t squared minus 2t plus 1.
Okay, limit examples. Evaluate the limit or explain why it does not exist. 8. The limit as x approaches 4 of the function x squared minus 4x plus 1. So we can simply plug this 4 in. There should be nothing that goes wrong by just plugging this 4 in. So 4 squared minus 4 times 4 plus 1. 4 times 4, 16, minus 4 times 4, 16 plus 1. So the limit as x approaches 4 of this function will equal 1. Question 8, simple, about as simple as it gets. 9. Number 9. 9 is a bit trickier. We can see here that the limit as x approaches negative 2 of the function x squared plus 2x over x squared minus 4. If we plug minus 2 directly into the function, we get negative 2 squared plus 2 times negative 2, negative 2 squared minus 4. Negative 2 squared is positive 4. Positive 2 times negative 2 is negative 4. So on the top we get 0. On the bottom we get negative 2 times negative 2 is positive 4 minus 4, 0. 0 divided by 0 is undefined. You cannot take 0 things and divide them into 0 groups. It sounds like you can, but you can't. So you cannot just plug this in. We need to do a little bit of mathematical trickery. So we know that this function, x squared minus 4, is reminiscent of x squared minus some value x minus 4, something like that, which we know comes from foiling where we add x times x to get us the x squared, and then we'd have x times some value to get us the middle terms, and then finally the last terms, which should get us minus 4. To get minus 4, we'd have to have a positive 2 and a negative 2. And then it makes sense why this term disappears. X times negative 2, negative 2x. The middle term, positive 2 times positive x, so plus positive 2x. These two terms cancel. So x squared minus 4 is x plus 2 times x minus 2. So we can write the limit as x approaches negative 2 of, and we can also take an x out of this top term and say x plus 2 over x plus 2 times x minus 2. We can now see that this term here and this term here cancel. And now we can plug, get an eraser here. Now we can plug the negative 2 in. We would get negative 2 over negative 2 minus 2. It's negative 2 over negative 4. Those cancel. You can divide 2 from each of those. 1, 2. And you get yourself a limit of a half. Okay. Done that one. Ten. The limit as x approaches 9. Limit as x approaches 9 in the domain of the function x squared minus 3 over x minus 9. Now this function has the exact same properties as this function. However, this function has been reduced 1 extra. It's such that this term is in a square root rather than just being, say, when you take the x out in the x plus 2 form. We've gone 1 more. But this function here then, if it's got the same properties, x minus 9 should therefore be able to be FOILed, such that our two values are the square root of x, such that the square root of x times the square root of x equals x. So we're halfway there. And then negative 9. What can we do that has negative 9? That's a positive 3 and a minus 3. Look what we have over here. That would get us a negative 3x squared, a positive 3x squared, and a negative 9. These two terms cancel, and that is true. So we can say that the limit as x approaches 9 of the function the square root of x minus 3 over square root of x plus 3 times the square root of x minus 3. These terms cancel. We're left with 1 on the top. The limit as x approaches 9 of 1 over square root of x plus 3. We plug a 9 in. 9 squared is 3. This gets us 1 over what's 3 plus 3? That's 6. So, question 10, 1/6. Question 11. The limit as h approaches 0 of the function h plus 1 squared minus h minus 1 squared over h. Clearly, if we plug the 0 in, we instantly have a problem. We will be dividing by 0. I don't really care if the top comes out to 0. I'll be dividing by 0 either way, and I don't like that. So, what are we going to have to do? We are going to have to FOIL both these terms and see if we can reduce anything. So, the limit as h approaches 0 of, let's FOIL the first one. H times h will be h squared. And then what will we get? H times 1. And then 1 times h, 2 h's. Positive 1 times positive 1 plus 1. That's our first term. Minus, do it again, but it should be in negatives. X, or h squared, negative 2h, and a positive 1, because negative 1 times negative 1 is a positive. All over h. This negative is the same as saying plus negative 1 times all of this. So negative 1 times h is negative h. That negative 2h would get positive, and this 1 would get turned into a negative. There. Now we can do this. We can remove the brackets. And we can add across. Positive h squared plus negative h squared cancel. Plus positive 2h plus positive 2h is 4h. So let's write the limit as h approaches 0 of 4h. Positive 1 minus 1, those cancel. So we have 4h on top, h on the bottom, the h's cancel, and we approach 4. Okay, last one. 12. The limit as t approaches 1 of t squared minus 1 over t squared minus 2t plus 1. Let's try plugging Let's try plugging 1 in and see what we get. So that's 1 squared minus 1. 1 squared minus 2 times 1 plus 1. What is 1 squared? 1. 1 minus 1, 0. 1 squared is 1. Minus 2 times 1 is 2. Plus 1. 1 plus 1 is 2. Minus 2 is 0. So if we plug it in at this stage, without simplifying, we have an undefined term. We're not quite sure. We need to work this out. So, what do we have here? We have two different terms, both of which have the form of having been FOILed. This is a completed FOIL where the middle terms obviously canceled. And we were left with just the outside terms. And in fact, this should be the FOIL, because what else is going to get us minus 1 but plus or minus 1s? So in that case, that would be a t squared. This t squared, we'll actually go t minus 1, t plus 1. So the limit as t approaches 1. On the top, we should have t minus 1, t plus 1. On the bottom, we have a term which is halfway through being FOILed. I always put to get in this car. Okay, and on the bottom term, we have one that is in the midway process of being FOILed. So we should have a t times something and a t times something. So what would times to positive 1 but would add to negative 2? Well, a negative 1 can do that, because that's t squared. T times negative 1 is negative t, positive 1, t squared minus 2t plus 1. Confirmed. So on the bottom, t minus 1 times t minus 1. We can see here that we have two terms that can be cancelled, leaving us with the limit. Just erase it. The limit as t approaches 1 of the function t plus 1 over t minus 1. This is the lowest terms. We can't reduce any further, so we have to plug in 1 and see what we get. And we get 1 plus 1 over 1 minus 1. And we get 2 over 0. This remains undefined. So we can say that the limit as t approaches 1 of this function does not exist. And we can explain that by saying, once we've reduced this to the lowest terms, and we plug in the value, we still find that it is absolutely meaningless. There is nothing here to define. There is no limit. It does not exist. Okay. So we give this a little check, and we are done.
Limits at infinity. We say that f of x approaches the limit L as x approaches infinity. We write the limit as x approaches infinity of f of x equals L. If the following condition is satisfied, for every number epsilon greater than 0, there exists a number r, possibly depending on epsilon, such that if x is greater than r, then x belongs to the domain of f, and the absolute value of f of x minus L is less than epsilon. For example, the limit as x approaches infinity of the function 1 over x will equal 0. Likewise, we can flip this function and find infinities as the limits. The limit as x approaches 0 from the left of f of x, we find negative infinity. The limit as x approaches 0 from the right of f of x, we find positive infinity. And therefore, we also find that the limit as x approaches 0 of f of x does not exist.